So good afternoon and welcome to today's communication signal processing seminar. Before I sort of introduce the speaker for today, I should thank Sherry Falkamp and Kate Godwin, who do all the work behind the scenes to make the seminar happen. So it's my pleasure to introduce Gauri Joshi, who's our speaker today. So Gauri is an assistant professor in the EC department at Carnegie Mellon University. She's been there since September 2017. Before that, she worked as a research staff member at IBM T.J. Watson Research Center. Gauri got her PhD from MIT ECS in June 2016, where she was advised by Greg Warnell. But she also worked a lot with Emina Soganen on some load balancing with coding problems around her PhD and after that. She received her BTech and MTech in electrical engineering from the Indian Institute of Technology, Mumbai in 2010. She has received several awards for her research, including the NSF Career Award in 2021, which is recently, the ACM Sigmetrics Best Paper Award last year, at the NSF CRI Award, CRI Award 2018, IBM Faculty Research Award 2017, the Best Thesis Prize in Computer Science at MIT in 2012, and the Institute Gold Medal of IIT Mumbai 2010, which for those who don't know, it's usually the student who has the highest GPA in the whole institute. Anyway, with that, I cede the floor to Gauri. Please go ahead and
Thank you. Thank you so much, Vijay, for the generous introduction. I'm happy to give this talk at UMich. Thanks to the seminar organizers for inviting me and also setting up all the meetings. Good afternoon, everyone. I'm very excited to present this work on communication efficient optimization methods for federated learning. The communication efficient part is key here because there is an increasing interest in running machine learning training on mobile or edge devices. And that is the new paradigm of federated learning, which is becoming very popular in machine learning literature. So in today's talk, I'm going to first start by introducing federated learning for those who may not be familiar and to show how it differs from traditional distributed machine learning. And then I will talk about two pieces of work on communication efficient optimization methods. Both these works are led by my PhD student, Jianyu Wang. And for the second work, which was recently presented in NeurIPS, we collaborated with Tsinghua and Professor Vince Poor from Princeton. I also want to acknowledge funding support from NSF, Qualcomm, IBM, and other sources, without which this work would not have been possible. So since this talk is about machine learning training, I want to start by mentioning stochastic gradient descent because machine learning training is pretty much synonymous to using stochastic gradient descent. It's the most widely used algorithm. It's, for example, the backpropagation algorithm used in neural network training is a special case of SGD. So SGD, at its core, it's a simple iterative algorithm. Because of its simplicity, probably it's so ubiquitous in machine learning. So it takes in machine learning, the objective function takes the form of this empirical risk function, which is an average of the losses at different data points in the training data set. So there are capital N data points. Psi here denotes the index of the nth data point. And this is our objective function. And SGD minimizes this objective function by drawing a batch of B samples in every iteration, computing the gradient for those B samples, and then taking a small step along the direction of steepest descent. So eta here corresponds to the step size. And X is the model parameter vector, which contains the weights and the biases of a neural network if you're doing neural network training, or the parameters of some other model that is being trained. So as you can see from this equation, SGD is inherently sequential. But for large data sets, if this capital N is really large, it is prohibitively slow to use this sequential update rule and perform and pass through the whole data set. So it is imperative to distribute the computation across multiple nodes, which is what is done in most industrial implementations today. So SGD is typically implemented in a distributed data center setting by launching different servers in the cloud. So there's one server called the parameter server that is dedicated to aggregating and hosting the current version of the model, which we denote by XK. And there are M worker nodes, among which the training data set is shuffled and split equally. So in each iteration of synchronous distributed SGD, these workers would read the current version of the model parameters. Then they would sample one mini batch of data from their local data set and compute gradients, which are then sent back to this parameter server. And then the parameter server aggregates the gradients together, takes an average of the gradients, and then applies that SGD update rule. So the model parameter vector goes from xk to xk plus 1, and then this whole process repeats. So a key thing here is that in this standard distributed setup, the parameter server has to wait for all the nodes to return their gradients. So ideally, if we have more nodes, we are processing more data per iteration, and we would like to get an M-fold speed up in achieving the target accuracy. But in reality, we do not get that M-fold speed up because this is a real system that encounters synchronization and communication delays. So in particular, if you look at the timeline at which this algorithm is run, if you consider these M workers and the horizontal axis here is time, the arrows denote the computation time locally at the workers, then in each iteration, you have to wait for the slowest workers to finish. That can be a bottleneck. We have done some work on these lines on changing the synchronous aggregation process to asynchronous SGD. But I'm not going to talk about that today because today my focus is on communication efficiency. So I'm going to focus on addressing this communication delay, which is the time spent in aggregating gradients from these worker nodes and updating the model parameter and sending back the model parameter to the workers. So how do you overcome the communication delay? One solution that is very effective is called local update SGD. So as the name suggests, what you do is instead of these workers just computing and sending gradients after every single iteration, they do independent local updates to the model. So each worker will take tau steps of SGD using their own local data, and then the model will be aggregated by the central server. And this process will repeat. So clearly, this will reduce the frequency of communication and as a result, make the algorithm more efficient. It also has an effect on the conversions. So we have looked at it in some of our work, and several others in recent literature have studied this problem of local update SGD. So to summarize, what I mentioned are just two ways of addressing the, the scalability of SGD in the parameter server framework. But in spite of these methods that improve the scalability, there are some limitations of using this data center based framework. The first is that all these workers, they're typically homogeneous and they have to be available throughout the training process. So if some worker drops off, then this process could become unstable potentially. And secondly, and more importantly, what we really need to run training in this setting is that we have to have the entire training data set available in the cloud. And then this training data set has to be shuffled and then evenly partitioned across the workers. So the availability of a central training data set breaks down as in recent applications because there's enormous amounts of data collection at edge devices. So most of us who use smartphones are generating lots of informative data whenever we use applications on our smartphones or tablets or even IoT sensors. And these data could be used to train informative machine learning models. So for instance, whenever we type something on the phone's keyboard, there is a service that predicts the next word that we will type, and language models are often used to do this prediction. So if we wanted to implement this kind of prediction service or some other application using data collected at the edge, a naive approach would be to send all of this data to the cloud and then run machine learning training in the parameter server framework, which I just mentioned. But sending raw data from thousands of devices to the cloud can be very expensive and slow. And moreover, there can also be privacy laws that forbid data sharing with foreign servers. So it may not even be possible for these devices to upload their data. So how do we learn informative models under these constraints? That's where federated learning comes in. So recently, starting 2017, there's an enormous amount of interest in doing federated learning, which means that you bring the training to the edge. So the data that these edge devices collect stays on the device, whereas the model training is moved to the edge. So to put it more concretely, what happens is that each edge client or each mobile edge device performs several local SGD updates by taking the current version of the model from the cloud, doing local updates, and then sending these updates back. So what you can see here is that these arrows represent transfer of the model rather than the data. So because the model can be represented in much fewer bits than the entire training data set, this method gives better communication efficiency, and it also gives better privacy guarantees than transferring all training data to the cloud. So this architecture is already being used for the next word prediction application that I mentioned earlier on Android cell phones. So Google is using this in production, and there's enormous amounts of work over the past few years exploring other applications of this federated learning paradigm. So at a high level, if you look at this picture, it might seem that this is pretty much the same as the parameter server framework. There is a central server and there are these worker nodes that have different portions of the data set. But there are some subtle but important differences between the federated learning setup and the data center based setup. So one important difference is that the data that are stored at these nodes are inherently heterogeneous because this data is being collected by the edge device rather than it being a shuffle partition from a central data set. So each device can have different amounts of data as well as very different composition of data. So if two devices are in different parts of the world, then the way they use the application and how they generate data can be very different. So that is one difference. Secondly, the computation speeds of these clients can vary widely because some clients might be mobile phones, some clients might be tablets or IoT sensors, and depending upon the type of the device, the speed can vary quite a lot. And another thing is just the scale of the system. So that in this federated learning framework, there can be thousands or even millions of geo-distributed devices, whereas in the data center setting, there are generally tens or at most hundreds of workers that are used to perform the parallel machine learning training. And because the number of devices that participate in this training process is so large, only a subset of these clients are available at any given time. So each round of federated training will consist of only partial subset of these devices. So next, let me talk about the algorithm used for federated training more concretely. First of all, let's talk about what is the objective function here. So since each client has their own data set, the local objective function at the ith client is denoted by Fi. This is just the empirical risk function for that client's local data. The global objective function, the standard form that is used in most literature is that it's the weighted average of these local objective functions, where the weight is the fraction of data that is present at the ith client. So a client with more data gets higher weight in this weighted average. And the reason that this weight is chosen to be PI is because we want to emulate a centralized training scenario where this data could be pulled together in a single training data set and we would run training on it. So since that is not possible in the federated training setting, the data is inherently distributed. We want to make sure that the objective function emulates having a collection of all these data sets. So the goal is to find the parameter vector x that minimizes this global objective function. But the way we are going to go about it is that since there is no central access to the whole data set, we won't be able to directly run gradient descent on this global objective, but rather the clients will run local SGD on their own objective functions and we will aggregate their updates. So in each communication round or in each training round, the current version of the model will be sent to whichever clients are available. So the current version of the model is denoted by XT here for the Tth communication round. And then these clients would perform tau local updates using their local data. So after those tau local updates, you can see that the model versions at these clients will differ from each other. Since they have different heterogeneous data sets, they will end up with different versions of the model. And then these updated models will be aggregated by the server. In this way, the clients will just send back the models and then they will be aggregated in proportion of the fraction of data that is there at the ith client.
Gauri, a quick question here. You're assuming that all these clients take the same amount of time to do the tau steps.
Not necessarily. So I'll come to that later on also, but we are assuming here that each client does tau steps. Maybe some clients take longer, but the central server will wait for all the clients. So these are a subset of clients of out of those thousands or millions. So it is okay to wait for all of them to finish.
Okay.
But you could consider straggler resilient variants of these where you wait for only, so you say 100 clients are participating in this training round, you only wait for 50 of them to finish the tau steps.
And there is no way that you, I mean, another thing that you can do, and I was going to ask this question earlier itself, is that if I know I'm going slow, but I have my data set is rich in certain variables, I only compute the gradient for those variables and give you that, as opposed to because of the linearity part. So I mean, that way I'm giving you effective gradients for things that I know well, and I can do that fast. I'm not asking you for the entire gradient vectors. Are there schemes of that kind that you can, are used or not used?
So partial updates to the models are used in the context of data center setting, but I think what is more commonly used to solve the problem of computational heterogeneity is that some clients just do more local updates than the others.
Well, if you're aggregating in a linear way, it shouldn't matter. If you get partial updates of certain variables, it doesn't matter. Right? In the sense certain other variables are held constant.
No, but the different parameters of the gradient vector can be dependent on each other. So you cannot independently find updates.
Well, I'm saying if you look at my gradient, I'm only focusing in certain directions. So so there must be some, we can talk about this afterwards.
Okay, sure. So yeah, there are different ways in which you can make this process more straggler resilient. One is that, you could consider either fewer updates or look at smaller mini batches. There are many ways to do that. So I'm just describing the vanilla framework. And in fact, I'm going to go into some of these modifications in the rest of the talk. Thanks for the question. I'll be happy to chat offline. Okay, so now that you all know this algorithm, let me give a brief outline of the rest of the talk. So the first question that I want to answer is, how do you choose this tau, the number of local steps that are done at each client? Because the choice of tau can affect not only the accuracy of the final model, as well, it will also affect the speed at which you get there. So that's going to be the first thing that I talk about. Secondly, we want to think about what happens when tau varies across different clients because of computational heterogeneity. And for simplicity, in this talk, I'm going to assume full client participation. That is, all the clients participate in each round of training. But the results can be extended to partial client participation whenever the clients are sampled at random from the total set of total set of clients that are participating in the federated learning framework. So let me start by talking about the choice of tau and how data heterogeneity can affect the performance. The first thing that we want to think about is, how does tau affect the speed at which you converge? So we expect that as you increase tau, because each client is doing more local computation and less frequent communication, the number of iterations that you finish, the number of iterations being the number of steps in total that we take, will obviously be better if you have larger tau. So within each communication round, you perform more iterations of local training. So collectively, you will do more iterations and as a result, converge faster. But as you increase tau, these models that are being trained at the clients can also diverge from each other, because each client has a different data set. So the models can go off in different directions. And that can cause issues with the solution that you converge to. So let me talk about how tau affects the final solution by using a toy example. So let's consider an example of just two clients. The first client has the local optimum x1 star. This is the minimum of its own objective function. And this is the second client's local minimum. And x star is the global minimum of that overall objective function, which is a weighted average of the local objectives. So starting from the model xt0, suppose consider the tau equal to 1 case, where each client is just doing one local update. So each client will move roughly in the direction of its own local minimum, depending upon the direction the stochastic gradient gives it. And then these updates will be averaged, and you'll get this averaged model at the central server. And we'll repeat this process. So eventually, because this averaged gradient is just a linear combination of the local gradients, this average gradient will be consistent with the global objective, and we will move towards the global minimum that we want to reach. So the true global minimum is here, and eventually if we run this process for enough number of rounds, we will reach that global minimum. So tau equal to 1 is not a problem at all. It's equivalent to doing just vanilla SGD on the global objective. But if you consider the other extreme, suppose tau is large, then things can go wrong. So if tau is very large, each client can do many local updates, and then they might reach very close to their own local minima. So client 1 reaches close to x1 star, client 2 reaches close to x2 star. And then if we take the average of these, we'll end up here. But now what happens in the next round? In the next round, each client will again go to its own local minima, and then the average will again come back to this black dot. And basically you're stuck at this point. So because the average of the local minima is not necessarily equal to the global optimum, because the f of x is not a linear function, we can get stuck at the average of the local minima rather than reach this x star global optimum point that we intended to achieve. Is that clear? Are there any questions about this? Okay. So putting these two together, what we see is that if you look at the convergence in terms of the training loss versus the number of communication rounds that you take to converge, using a smaller tau gives us a consistent solution because we end up optimizing the global objective itself. But using a larger tau gives faster convergence since we do many more iterations in the same number of rounds. Although with larger tau, we can get a higher error floor because the solution that we get can be away from the x star, the global minimum that we wanted to achieve. So how do you find the best of both worlds? How do you get a better trade-off? Some existing solutions are that we choose small enough tau, or we reduce the learning rate at the local clients. Or there are also proximal methods that can be used that pull back these local updates so that they don't stray too far away from the global model. So all of these methods, while they do improve the consistency of the solution, so they will give us a low training loss, they will slow down conversions. So instead, what we propose is using an adaptive tau to get the best of both worlds so that we can achieve something like the dotted line here, where we start off with a large value of tau, because even if at the beginning you're roughly moving towards the global minimum, that's fine. But then towards the end, you want to have a small value of tau so that the updates are in the direction of the global optimum and we achieve a low error floor. So how do you come up with this adaptive schedule? The first thing to do is try to characterize how exactly the error changes with respect to communication rounds. So in one of our papers, we obtained this error bound on the training loss after T rounds. And there are two terms that are more important in this bound. The first is this term that decreases with tau. So this tells us this the conversion speed, like how quickly this curve drops off. And then this term, which is this final error floor term, increases with tau. So in order to find the best possible tau at any given time, what we can do, a heuristic way, is to optimize this upper bound on the error with respect to tau. So for a given number of communication rounds, so we can actually divide these communication rounds into different intervals of T0 rounds each. And at the beginning of each set of T0 rounds, we change the value of tau. And by optimizing this bound and making some approximations to remove terms that are unknown, what we get is the tau is approximately equal to the square root of the objective function at that time divided by the objective function at the beginning times t naught, which is the initial tau that we select. So how do you select the initial tau? That can be done just by grid search. And then once we know the initial tau, we can use this update rule to change tau as we go along. So this tau schedule tracks the progress of the objective function. So whenever the objective function reaches a low value, it's going to reduce tau in order to get a better error flow. So gradually, this schedule will reduce tau over time and hopefully get us close to this dotted line that gives us the best of both worlds. So although this is a heuristic schedule because we are optimizing the upper bound, in practice, we observe that it performs pretty well. So these are some experiments on using this adaptive tau scheme for the CIFAR10 dataset, which is trained using two different neural networks with a system of 4 clients. And the plot here shows 3 different fixed tau schemes, comparing those with this adaptive communication scheme. And the bottom plot here shows how the optimal tau changes over time. So the optimal tau reduces over time as we expect. And the adaptive scheme gives fast convergence at the beginning, but also low error flow at the end. And similarly, even for ResNet, we get a good performance using the ADACOM scheme. And in particular, in this example, the ADACOM scheme does almost 3 times better in terms of the time taken to reach a particular level of training loss. So the takeaway from this first part of the work that I presented is that the choice of tau is important in order to make sure that we don't get an inconsistent solution, and adapting tau during the course of training might be a good way to get fast conversions as well as a consistent solution. So next, let me talk about what happens when tau varies across clients. So where does this heterogeneity come from? There are several sources from which we can get computational heterogeneity. When I told you about the federated learning algorithm, I said that each client does tau local updates, but in practice, often the way federated learning is implemented is that each client does the same number of local epochs, not the same number of local updates. And one epoch means one whole traversal of the local data set. So if a client has NI samples in its local data set, then the number of local steps that it would take will be equal to E, the epochs that it does locally, times NI divided by the mini batch size. So clearly, clients with more samples, they will do more local updates. And as a result, in every round, we will have this asymmetry in the amount of local work that clients are doing. Another source of heterogeneity could be a straggler resilient version of federated learning, where in order to take into account the fact that some clients are slower than others, the system designer might choose to aggregate their updates after a fixed time window. So they may fix a time window and let the faster clients do more updates and the slower clients do less updates and just aggregate them. And thirdly, even if the number of local updates are fixed across all the clients, they may use different local optimizers. They may use different learning rate, momentum, or they may use some adaptive optimizer, which can cause the amount of progress locally to be quite heterogeneous across clients. So although these sources of heterogeneity are known, the current algorithms and implementations actually disregard this and aggregate the client's updates, just like we described earlier, in proportion of the local data set sizes. But this kind of naive aggregation can cause some serious consistency issues. So what we can show is that heterogeneous local progress can cause objective inconsistency. And what I mean by objective inconsistency is that we might end up optimizing not the global objective function that we started off with, but some other objective function that depends on how much heterogeneity is there. So let me show you what this means through an example. Let's consider a homogeneous setting where you have, again, just two clients which have these local minimum, and this is the global minimum. And we start off with this model. Suppose both clients do two local steps, then we average them, and our global model moves to this point. So as long as tau is small enough, or the learning rate is small enough, we will end up reaching this global optimum x star. But instead, suppose we have a heterogeneous setting where the first client here does many more local updates than this client. Then if we just naively take an average of these two updated models, then this averaged model will be biased towards the client which has more local updates. So if we repeat this process, this client will move, this model will move closer to this local optimum and further away from x star, which we intended to reach. So how can we characterize, how do we know exactly where this model ends up with? We can actually show that the homogeneous setting will end up with a convergence point that is a stationary point of the global objective. So this is the intended point that we wanted to go to. But this heterogeneous setting corresponds to optimizing a mismatched objective, which is given by x tilde. So instead of optimizing f of x, we are optimizing this f tilde objective function where the weights assigned to the clients are dependent on the number of local updates. So as you can see, clients with more local updates will get a higher weight in this aggregation. So we'll get an inconsistent solution as a result. And this objective can be arbitrarily different from the true global objective. So how do we fix this problem? How do we make sure that we are moving towards this global optimum rather than going off in a wrong direction? One easy and obvious way is to correct the weights that are used for aggregating these client updates. But coming up with the correct weights is not that easy. So we found out that you have to come up with a generalized version of the federated learning update rule in order to find these correct weights. So let me show you the corrected version that we came up with. So this corrected algorithm, we call it FedNova, or federated normalized averaging. The way it corrects the aggregation weights is that it starts off, let's start off with just the vanilla federated averaging update rule with heterogeneous client. So suppose this first client does 4 local updates and the second client does 2 local updates. Then what the clients are sending back to the server is this accumulated gradient, the delta 1 from the first client and delta 2 from the second client. So this is the total amount that these clients move. And then the global model, this blue arrow, the update to the global model, is an average of these delta i's that are sent by each of the clients in proportion of pi's. So as we saw earlier, if there is heterogeneity, this update rule optimizes a mismatched objective function. So the way to correct it is that instead of averaging these accumulated gradients delta I, what we should be averaging is normalized gradients. So we go back to this picture, but now instead of the client sending delta I to the server, it should send delta I divided by tau I, where tau I is the number of local updates that it does. So these green arrows are what we average instead of the dotted blue arrows. So the server will average these green arrows and get the direction in which the model should move. Now you might think the magnitude of these updates has reduced, so won't it slow down convergence? The answer to that is that we can actually scale up the aggregated update to make sure that the convergence is not slowed down. So all we are doing is correcting the direction of this arrow rather than the average magnitude. So the FedNova update rule, it looks the same, similar to federated averaging. The difference is that the weight assigned to the ith client's accumulated gradient is pi divided by tau I instead of pi by itself. And this tau effective is a scaling factor that makes sure that the length of this aggregated model is not, this aggregated vector is consistent with how much you would move in the original case. So we can show that this update rule corrects the bias and it makes sure that we are optimizing the true global objective function. So I'm showing here the correction for vanilla SGD, but while we are trying to come up with this corrected, these corrected weights, we developed a generalized way of expressing the federated learning update rule. So the federated learning update rule, it could be modified to this form, which has three key parameters. So let me explain to you what these are. The first thing is the normalized update. So instead of sending the accumulated gradient, we are sending this gradient, the accumulated gradient divided by tau in the case of federated averaging. But in general, this green arrow could be any arbitrarily linear combination of the local gradient steps. So we allow for any such linear combination in this generalized update rule. Secondly, you have these aggregation weights, WI, which determine how these green arrows are averaged to get the direction of the blue arrow. So this is what the server multiplies the normalized gradients with to get the aggregated model update. And lastly, there is the effective steps per round, which is used to scale up or scale down the average updates. And this can be treated like a server learning rate. So the nice thing about this generalized rule is that by changing these parameters, we can get several special cases, including the original federated averaging, the FedNova scheme that I described, also other variable learning rate and momentum schemes. And we have a unified convergence analysis that covers all of these algorithms and gives new insights on their convergence. So a special case of this scheme is where you set all of these AI parameters, the linear combination parameters to 1 over tau. That way you'll just send the sum of all the local gradients. And if the aggregation weights are this way and the effective number of steps is this, then we get back the vanilla federated averaging algorithm. So all that FedNova does, this modified scheme that we came up with, is that it changes these aggregation weights to pi in order to make the surrogate objective consistent with the global objective. So some experimental results. These experimental results compare Fed averaging an algorithm called FedProx, which was designed to remove inconsistency, and FedNova. This shows the training loss versus number of communication rounds for a case where tau I are consistently different across the client. So if the client 1 takes 4 local updates, client 2 takes 2 local updates, then they just continue taking that same number of local updates in all communication rounds. So what we see from this plot is that Fed averaging gets stuck at some point here. It does not go down further. So even if we extend this curve further, it's going to get stuck at a solution that does not match with the global optimum. But FedNova can, first of all, it converges, it preserves the convergence speed of federated averaging, but it also converges to a more consistent solution. And similarly, even if the number of local updates are random across the communication rounds, we get a similar gain with FedNova. And another nice flexibility with FedNova is that it is not restricted to using vanilla SGD as the local client optimizer. So even if the clients use something like a momentum optimizer or proximal gradient or a variance reduced local optimizer, FedNova only changes the weights assigned when aggregating the updates. It can keep everything else the same. So just by tweaking those weights, what we can see is that for all of these optimizers, the performance, the test performance is either preserved or improved significantly. So for example, if you look at the proximal gradient row here, instead of the Fed averaging aggregation, if we do this corrected weighted aggregation, then we see a 10% boost in test accuracy. So key takeaway from this is that it is important to take into account the heterogeneity in the local progress and not just aggregate updates in proportion of data size. You should first normalize them and then aggregate them in proportion of the data size. So with that, I want to wrap up and summarize what we talked about. So federated learning is this new distributed learning paradigm that is posing lots of unique challenges. And this is a new research area. So there are many open directions that are left to address. So some challenges that are specific to federated learning include strict communication limitations because you're working with resource limited and bandwidth limited edge devices. Secondly, data heterogeneity. So today we saw how adapting tau could address the combined effect of both of these. Another issue is computational heterogeneity. We showed this FedNova scheme that corrects for the effect of computation and data heterogeneity. Another interesting direction is to consider partial client participation and try to see whether we can select the clients in a smarter way to get better convergence. Also, privacy, fairness, robustness, and many more issues are still being actively researched, and there are lots of open challenges along these directions. So with that, I want to conclude and just show the archive links of the papers that I covered during this talk, as well as some other papers on distributed SGD that came out of our group. Thank you, everyone. I'll be happy to take any questions.
So Gauri, so what I'm going to do is let Sue, who's going to be the discussant, go, and then I'll open it up for questions. So maybe if you can stop sharing, and he can share next. Yeah.
Sounds good.
Hello.
Yeah, I can hear you.
Okay. Yeah. So let me briefly summarize the work. So actually, they have 3 papers, and this one is not intensively covered in the talk. So maybe I can talk a little bit about this. So this work, cooperative SGD, they they present a unified framework that incorporate existing communication efficient SGD methods as their special cases. So there are 4 existing methods, which includes the fully synchronized SGD, where just everyone compute the gradient and transmit to everyone, and everyone descend in the average gradient descent step. For periodic averaging SGD, you basically descend in your local gradient direction when this round is a multiple of tau. Otherwise, no. So you only do the averaging when the current time is a multiple of tau. Otherwise, you just do local descent. For elastic average SGD, they keep auxiliary variable z, and so this z works as a momentum to provide more stability, and there will be one additional alpha constant. And in decentralized SGD, this is like a distributed optimization setup where you may have some network, and the communication is it only happens between the neighbors in the network. So you can view this big X as a huge tuple of all the individual X and the auxiliary variable Z. And then you can use this update rule to incorporate all the 4 existing methods, where the tau will come in to this W matrix, where so this W matrix is like a mixing matrix, and so for for periodic averaging, this W will be identity matrix for all these non-averaging time index, while it will be a mixing matrix for when k is a multiple of tau. Also, so W is another variable dimension for the decentralized SGD1, where your mixing matrix could be arbitrary weights with second eigenvalue smaller than 1, and so this V is for the Z. So when you are considering elastic methods, then the averaging will also incorporate the Z part in this big variable X. So they provide the convergence analysis that's suggesting the trade-off between communication overhead and the error flow resulting from the model discrepancies. So using their analysis, you can also find the optimal alpha for the elastic average methods when you are minimizing the basically the spatial radius of that mixing matrix. Okay, so for the adaptive work, the basic concept is basically that the periodic averaging constant tau will control the trade-off between local computational time and the communication delay in terms of the runtime error. So intuitive way will be, because for the first few rounds you will expect you can do a lot in your local computation and do a lot of descent. And while in the later rounds, you will expect during the local computation, the gradient won't be too large. So in the later rounds, you might want to do more communication. So the idea is basically to gradually decrease the tau, and the objective will be to find minimize the convergence time. So for the heterogeneous work, so when the workers have a different tau that maybe resulted from heterogeneous computation speed or data or different data availability, basically what they did is to adjust the aggregating weight so that the correct objective is optimized. Because if you don't adjust that weight, those workers that have more updates will actually weighting the gradients larger. Okay, so I don't have any intuitive observations, so I just raised a few questions. So why the error rates monotonically with tau in your cooperative SGD work, while it's there's a trade-off term in your adaptive work? So is that because you introduce a communication delay in the adaptive work? So this is my first question. The second question will be, in your heterogeneous work, why do you choose a scheme that communicates the gradients instead of communicating the primal variable? So the mismatch and objective problem basically arise because you okay, say this worker gradient in this direction 4 times, but because you are communicating the gradients, so even how far it gets along this direction, it's not really useful because you are communicating the gradients. But if I communicated this point, then actually the mismatch and objective function mismatching problem won't arise. So I can give you, I mean, this is one example. So this FedPack algorithm is from our last year's CSP talk.
I'm familiar with this, yeah.
Yeah, so in their work, they communicate the X variable, so then the problem won't arise. So I wonder why you choose.
I think there's some misunderstanding here. Like so we are communicating the X variable here. It's equivalent whether you communicate the X, the final X, or the difference between xt0 and the final X. So because the central server already knows xt0, so if the central server knows, say, a variable A and you want to communicate B, either you can send B or you can send B minus A, and the central server will still be able to recover B, which is the updated version. So it's the same thing, like it won't solve the problem. Like, so FedPack, FedPack is solving a different problem altogether. FedPack is considering local update SGD, but trying to compress gradients when sending them. So instead of sending the difference between the updated model and the original model, they are quantizing it to further improve the communication efficiency. So this is, it's relevant to the federated learning problem, but it is orthogonal to what I presented today, because quantization could be used in addition on top of what I presented, which is basically just correcting the aggregation step here. So in the consensus step, that is the only step that we are changing. And we are changing the weight that is assigned to each worker. Does that answer your question?
Yeah. So my third, not really a question, is that I know there are some algorithms that they use another auxiliary variable y to basically track the average gradient. And I wonder if this could be a future direction where you use this variable to further maybe speed up the conversion.
Yeah, this is a good point. So there are some recent algorithms like scaffold, which have this control variable that tracks the average of gradients. So these methods do improve the convergence because these are reducing the variance in the gradients. And as I mentioned towards the end of the talk, this FedNova framework, it works with any local solver. So it also works with these variance reduction style methods. It can work with scaffold or other variance reduction methods. So this is a good suggestion. This will improve convergence and it can be used along with the techniques that I proposed.
Thank you. This is all my questions. Yeah.
All right, sure. So I'll open it up for broader questions. If you want to stop sharing, then you can.
Thank you for the discussion and the questions, Yusuf.
Hey, can I ask a quick question?
Sure, go ahead.
Yeah, sure.
Hey, Gauri, first, thanks a lot for this very interesting talk. So I have a question. So let's say if I have a two worker, one do one update, the other do like two updates. Can I send just the updates to the server so the server can like aggregate the first update from both worker first, then update the second, the second update from second worker? How would that work? Because that seems to solve the synchronization issue, basically become like some kind of stochastic gradient descent, update the parameter based on partial of the updates.
Okay, that's an interesting idea. So what you're suggesting is that instead of sending the accumulated update, you send updates individually.
Right. I just send all the updates I have, then the server can decide what server wants to do and how to aggregate them.
So yeah, you could do that. It might incur a lot of communication costs if you do many local updates. But if we keep that aside and just focus on convergence, then if there are heterogeneous number of updates, each step would be an average of a variable number of these gradients.
Right.
So that can introduce some additional variance in the gradients. But it will, I think it will solve the inconsistency problem at least.
Yeah, so I think the advantage is it may not have the inconsistency issue here. Yeah, okay.
So Gauri, I had a quick question on the, when you take multiple steps, you mean you're taking you're reevaluating the gradient, right? Every time you do that, and at least locally. So
you reevaluate gradients, but at different points. So you take one step.
Yeah, I know, that's what I'm saying. So your assumption in some sense is the function must be smooth enough, right? I mean, there'll be a lot of smoothness in the function for it to make, because if I am taking 100 steps and if the objective function was not smooth, then basically, or it was basically had the gradient was varying quite a bit, or the second derivative was varying, Hessian was varying a lot, then basically one algorithm will move very far, and in some sense will do a lot very different, and the other one that takes 2 steps will do something very local. And so in some sense, there's an assumption here that you're doing everything in a local sense, and it's okay to aggregate.
For the convergence analysis, yes, we do need a smoothness assumption on the local objectives, as you say.
So what happens if you don't have smooth?
Without smoothness, it's hard to give guarantees for SGD convergence. So even the classical results.
Because you can come up with there's basically sometimes there's a decomposition thing as well, right? I mean, if you're assuming there are different objectives, Fi and so you can your some objective may be smooth, but the ones that you're given to different workers may not be.
I see. So here we are assuming that all of them are smooth.
Okay.
Which Yeah, if they are not smooth, then gradient descent locally, at least it will have problems converging.
Okay.
Mhm.
Any other questions from anyone?
I see a question in the chat.
There was, I think,
Oh, I think this is a direct message to me. Somebody asked a
yeah.
question in the chat asking whether the step size is fixed for each update throughout all the workers. So that's a good question. For the first part of the work that I presented and second part also, like we consider that the step size is constant, but then the generalized update rule that I proposed at the end, that works even if the step size is variable across clients, and even within a client over time, the step size is allowed to change.
So some of the weighting here needs to know, you need to know a lot about the data at every location, as in, need to know what fraction of data you have. And so as that becomes more uncertain, I mean, as your parameters here are uncertain, what happens to your algorithm? In the sense that you need to weight them properly, you need to know, you assume a lot of knowledge in some sense. Right?
So you only need to know the data size. You don't need to know anything else about the data set.
Okay. But that is something that the central server also needs to know, right? So
The central server does need to know that, but it will just be when it starts the communication round, the clients can tell what is the data set that they are working with. And also this is a static scenario where the data set is already collected. So it's not like data is arriving on the fly and then we are incorporating it in an online fashion. That would be interesting, but that is not yet considered.
And there is no noise in your setup in a way, in the sense other than the fact that you're just sampling the gradient.
Yeah, the noise comes from the fact that the gradients are stochastic. Also, there can be some added variance when only a subset of clients participate in each round. But there's no noise on the channel, if that's what you're thinking about.
Something like, because if you start weighting things by different parameters, then there could be, the noise could get amplified and things. And so I don't know if any of those things have been considered in your analysis.
So noise hasn't been, the noise on the communication channel, we are assuming that it will be handled by some error correction mechanism that is in place.
Okay. So there was another question on chat. I think you could unmute yourself and ask the question. So yeah.
Yeah, sure, I could. Thanks a lot for the presentation. As a non-expert, I really enjoyed it. So I'm just asking, this is more a philosophical question, but very important, I think, for any machine learning algorithm is, I see that federated learning seems to be solving a lot of issues of privacy and all that, but do you see as a researcher any potential, big picture social issues that could be caused by this process?
Yeah, that is a very interesting question. And this is an important issue, in fact. So the algorithm that I described to you, it considers that clients with more data set get more weight. Also, if the clients have intermittent availability, then only the clients that have more higher network connectivity, they will participate much more. So this can cause a fairness issue. If a client has very little data, if it does not have good network connectivity, it will contribute less to the global model. And then the global model that is being trained may not work well for that client. So fairness can be an issue here. There have been a couple of recent works on addressing fairness, but I think there's still much more to do. Like one way you can address fairness is by changing the objective function to give higher weight to these underrepresented clients. But that comes at the cost of maybe losing accuracy for the other client. So it's hard to find the right balance here. Related to fairness, there's also an issue of robustness. So if one client is adversarial, it's sending some bad updates, it's sending really high magnitude gradients that can like sidetrack the whole process and cause issues with convergence. So how do you overcome fairness and robustness issues is something that's interesting and still an open problem.
Thank you very much. That was very helpful.
So, thanks.
Any more questions from anyone? If not, let's thank Gauri for an excellent and stimulating talk.
Thank you very much.
All right. Thanks a lot, Gauri. Yeah.
Thanks for all the questions. Feel free to contact me if you have any more questions.
Bye.
Bye, everyone. Thanks again for hosting.
Thanks. Bye.
Thank you.
Bye.